This is Introduction to VLSI Design class, and this time we will talk about design for testability. We will talk about testing, including logic verification, silicon debug, manufacture and test. And then we will try to model the faults. We will talk about one of the simplest models. We will define the observability, controllability, and the fault coverage. And after that, we will see some of the design that makes circuits easy to be tested. It's called design for test. We will talk about scan and best, and then we will finish with the boundary scan. So testing is one of the most expensive parts of the chip design. Logic verification usually accounts for more than 50% of the design effort for many chips. The debug time after fabrication has enormous opportunity cost as well. So there is a good amount of cost for testing. Also, shipping defective parts can sink a company, and there are so many examples in history. One of them is the Intel floating point division bug at 1994. The logic error not caught until more than 1 million units already have been shipped to customers, and the recall cost was $450 million at that time. So we use actually the word testing and verification as equals, but there is some difference between them. Testing is actually making sure that the product or the system works after you have created the product components, chips, board, packages, and subsystems, and assemble everything together. Verification is making sure that the product or the system work before that, meaning before it has been created or manufactured. So if it is already assembled and ready to be shipped to the customer, the last step is to do multiple testings. Some of them are hardware testing, penetration testing, and many other type of testing. Before that, for every subsystem, within the subsystem itself, you do verification. You do it multiple times to make sure that what you are expected is the one that is implemented. And then while you are connecting the two subsystems together, for example, these two, you do another layer of verification and so on until you come up with the whole design. So in logic verification, what we want to answer is, does the chip simulate correctly? Usually this is done at the hardware description language level, and we have languages for this like Verilog and VHDL. The verification engineer writes test bench for these programs that can test all cases. If you want to test everything, you will spend a tremendous amount of time. You look usually for corner cases, and you do some penetration test where you try to break the logic design. This is an example, a 32-bit adder. You test all the combination of the corner cases as the inputs, like 0, 1, 2, 2 to the power of 31, minus 1, minus 2 to the power of 31. So these are the kind of the edges. And you can add a few random numbers. To see how they are really the edges, you can convert these numbers to binary, and you can see the string of bits, and you can see some of them are all ones. 0 is actually all zeros, minus 1 is all ones, and so on. So good tests require ingenuity, meaning you have to be smart of selecting these few random number of test vectors. In the silicon debug, you test the first chips back from the fabrication. And you try your luck. If you are lucky, they work the first time, and that's it. If not, then you need to do the debugging, stop the fabrication process, do the debugging, make sure that everything works, and then continue the fabrication again. To do debugging, you need to differentiate between the logic bugs versus the electrical failure. Most chip failures are logic bugs from inadequate simulation. Some of them are electrical failures, like the crosstalk, and we talked about this for wires, the dynamic nodes, like the leakage and charge sharing, and we talked about this before, like the ratio failures, and so on. A few of these bugs are actually tool or methodology failures, where the tool wasn't mature enough or the methodology wasn't done in the right way. So as we said, if you are not lucky, you need to do the debugging, you fix all the bugs and fabricate a correct chip and redo the test again for the first few chips until you get or you make sure that they work properly. In the manufacturing test, as you can see here, when you are doing the testing, it has to be a very clean room. It's actually as clean as the fabrication room. Sometimes it's actually part of the fabrication room. Why? A speck of dust on a wafer is sufficient to kill the whole chip. And the yield of any chip, no matter what, is usually less than 100%. It would be absolutely nice if you are approaching 95, 96, 97, and so on. You must test the chips after manufacturing before delivery to customers to only ship the good parts and avoid recalls. Manufacturing testers are very expensive, so you want to have a minimum you want to minimize the time on the tester, and you should carefully select the test vectors so you can cover as much failure as you can, or as much potential failure as you can. Here are some of the manufacturing failures. Like here, you can see that there is a metal one shelving. There is some cracks here. Here you have a bridging fault or a bridging defect. This is a metal 5 film particle. Here you have an open defect. Seems it's connected, but you see the black line here. This is actually an open circuit. This is a spongy via. It's in the stage of the infant mortality where it wasn't done properly. Here is a big miss. It's actually a patterning defect. This is a metal 5 blocked etching, and it caused this terrible problem. This is a spot defect, and they are very, very small. As you can see, there's one spot here, one spot here. Also here, you have an open at contact. It's supposed to be like this one. Even this one is not that good. It should be like really covering this circle where you can have a contact and the connection between the both layers. But here, it's not connected at all. It's only like at the edge, and usually this is an open circuit. Some of these pictures, they are or shown to you as a cross section, and some of them are is top view, like this one. It's top view. Now we need to test any circuit. We need first to understand the faults. So one step is to do the fault model. We will use the stuck at fault model. First, you need to worry about how does a chip fail? Where did the failure come from? Where are the faults? Usually the failures are either shorts between the conductors or open in a certain conductor. So we will use this simple model, which is a stuck at, where failures cause nodes to be either stuck at 0 or stuck at 1. Stuck at 0 means that you are the node is shorted to the ground, and stuck at 1 means that this node is shorted to the VD. This model is very simple model. It's not quite true. There is so many other faults, like for example, the one that we just talked about, the bridging fault. Those two lines are connected together. They're not supposed to be connected, not to VDD, not to ground, but it's a fault that you need to worry about. There is other models that cover these, but the simplest one that we want to study in this introductory class is the stuck at fault. So as we mentioned here, it's not quite true, but works well in practice. For example, if you have this circuit, it is actually implemented here. You can see that this is actually two input and, so they are series, and then parallel. The bubble means that there's a full bar and we can design in the pull down. These are two series, and the group is parallel. So the functionality is correct. However, one of the inputs here is stuck at 1, meaning that this input, this polysilicon, is connected to VDD. It's shortened to VDD, where it's not supposed to. The second input, for example, of this input is stuck at 0, meaning that it is connected to ground. It was shortened to ground. It will affect the output, of course, and there will be problems. So now, since we model the stuck, you simply shorten them to 1 or 0. This is the way of injecting these faults if you want to do a penetration testing. Now, for the observability, controllability, and the fault coverage, the definition for them, the observability is the ability to observe a node. This node is could be an external node, and many of the nodes, they are actually internal nodes inside the design. So how the ability to observe these internal nodes by watching the chip external output pins only is called the observability. The controllability is the ability to force an internal node to be 0 or to be 1 by driving the chip external input pins on. So notice that the observability, you work with the external output, the output that is really at the end, and the controllability is related to the external input at the very beginning. The fault coverage is the percentage of fault that can be detected during the test. Now, in the combinational logic and in the sequential logic, these, the observability and the controllability, could be really easy in a combinational logic. You can do it easily without any trouble, and we will have examples. In the sequential logic, especially if you have a finite state machine, this can be very difficult. It requires many cycles just to enter the desired state, and then you can do the test. This is difficult, especially if the state transition or the finite state machine is not known to the test engineer. So now we will talk about the test pattern generation. Manufacturing test ideally would check every node in the circuit to prove it is not stuck. And you apply the smallest sequence of test vector, and we call them test vector, which are the inputs that are necessary to prove that each node is not stuck, meaning not stuck at 0 and not even stuck at 1. So good observability and controllability actually would reduce the number of test vectors required for a manufacturing test, and in turn, it will reduce the cost of testing and also motivate for the design for test. And we will talk about this soon. So one of the actually first step to do the testing is to generate the test pattern, which are the inputs, the test vectors that you generate to make sure that you are doing the test correct. To get these test vectors, this is an example. This test example there's a question here. What is the total number of a single stuck at fault, counting both the stuck at 0 and stuck at 1 in the following circuit? And I give you this simple circuit. So for each line, you should count 2 faults. One of them is the stuck at 0 and stuck at 1. And you can see that's what I did here. This line, you have 2 stuck at 0 and stuck at 1, stuck at 0, stuck at 1, and so on, here, and here, and here, and here, and here, and here. Now, how many nodes you have? You can count them in this simple circuit. It's 1, 2, 3, 4, 5, 6, 7, and 8. 8 times 2 is 16. But let's say that you have a huge circuit. Can you get the total number of faults using the formula? Yes. This is the formula. It's actually 2, because you have stuck at 0 and stuck at 1, times the number of primary inputs, which is these ones, plus the number of gates. If you can't count all the number of gates, at least get an estimate. Plus the number of branches, if there are branches. The primary inputs here are 4, and the number of gates are also 4, and there is no branching. This is why we get also 60. Now, how to get the test vectors? How to get the test vectors? We will test every node. How? This way. Let's say that we will use or test the stuck at fault here. Stuck at fault here, which is stuck at 1. We will choose stuck at 1. How to do the testing? Basically, how to generate this row. Since we have N1, we will say, okay, this is N1, and we are trying to test stuck at 1. Find this test vector. How to find the test vector that will detect that there is actually a stuck at 1 fault in this line or at this node. So you start by writing with this format, true, and between parentheses, the faulty value. So we said that we are testing stuck at 1. So the faulty value will be 1, meaning that the true value will be 0. The true value will be 0. So the question is how to get 0, which is the true value here. So that's the first question. Also, the second question, how to make sure that you are propagating whatever value here all the way to the out. If you answer both questions, you will get all the bit values in all the lines. So let's start with the true value. The true value here is 0. To get a 0, actually you need 1 and 1 in this NAND circuit. So 1 and 1 will give you a 0. So now we have the 0 at this node. We need to make sure that it propagates to the out, meaning we have to put the appropriate value in the second line here. If we make it 0, it means whatever value here, the output here won't be affected by this line. And this is what that's what we don't want. So we have to make sure it's 1. If it is 1, then this node, the effect of this node will show up in the output. The reason is because we have a NAND. This gate is a NAND. If you have a 1, whatever value you have here, whether it is 0 or 1, if it is a 0, let me write it down. And let me also change the color. If you say it is 0 here, so 0 with anything in the AND will give you 0. After the bubble, it will always give you 1, no matter what's the value here. This is why it's not appropriate to have a 0 here. And the reason is because of the behavior of this gate. So what to do? We need to make sure it is 1. We need to make sure it's 1. To have a 1 in a NOR, you need to make this line 0 and this line 0. And a 0 is here. So you work your way backward. Since you have a 0 here and you have an inverter, this line will be 1. And now you know that if you put in the input 0, 1, 1, 1, starting from the least to the most significant bit, you can detect if this is a 1 faulty or not, because you'll just observe the output, the external output. And now here is the observability showing. You will observe the output. If the output is 1, there is no fault here. If the output is 0, then there might be a fault here, which is stuck at 1. Okay, I don't remember if I talked about this. So if you have 0 in the true and 1 in the faulty, and you have 1 here, you just work your way to the outputs. 0 and 1 in an AND circuit will be equal to 1. And the faulty will be the opposite, which is 0. This is why we write down 0, 1, 1, 1. Now, what if we test the same node, but stuck at 0? Now the true value is 1, the faulty is 0. Again, we have the same scenario here because you want the value here to be 1. So it will be 0 here, 1 here, and 0 here. Similar like the other case or the previous case. But now here, this one in an AND could be generated in multiple ways. Actually, in 3 ways. 0, if you put 0 and 1, or 1 and 0, or 0 and 0. All of these 3 possible combinations can give you a 1 here. And this is why you have a choice here and stuck at 0. You actually have 3 choices. Either you choose 0, 1, 1, 0, or 0, 1, 0, 0, or 0, 1, 0, 1. These are the 3 choices. If you do this test, stuck at 0 and stuck at 1, for all of the nodes, you can collectively get the set of the test vector that can cover the test or the whole test story. So we actually did that, but I didn't check or mention all the details. For node N1, this node, we did the stuck at 0 and stuck at 1, and we chose one of these 3 for the stuck at 0. And basically for N1, we chose 0, 1, 1, 0 for stuck at 0 and 0, 1, 1, 1 for stuck at 1. We similarly did the same for the 4 inputs and for nodes N3, N2 and N3, N2 and N3, and also for the output. And from these tests, or from these test vectors, we get the minimum set of test vectors to cover all of the stuck at faults. And we found out that for 4 inputs, we need to check only 6 inputs to make sure that the circuit works fine. If we didn't do this, we have to start from 0, 0, 0, 0, all the way to 1, 1, 1, 1, which is going to be 16 different combinations. Using this method, we need only 6 of them. So now, since we know how to generate the test vectors, and by the way, there are tools that can help you because there's a lot of work that you can do only for this simple gate. What if you have a bigger gate? So there are tools that can do this for you. Now, the design for test is what we mean by this, or actually the title of this talk. We said that design for testability. The design for test or the design for testability, meaning you design the chip or add some hardware to the chip to increase the observability and controllability, meaning to make it simply or easier to be tested. Now, we said that the sequential circuit test is difficult. If each register or a flip-flop could be observed and controlled, the test problem will be reduced to testing a combinational logic between the registers. So it becomes a combinational logic, which is easy to be tested. Not only that, the logic blocks could enter test mode where they generate test patterns and also report the results or the signatures automatically. To understand this better, this is what actually we call the scan test. The scan test, in the scan test, what we do, we convert each flip-flop to a scan register. So if you have a sequential circuit, basically you have a combinational logic followed by flip-flops. Combinational logic followed by flip-flops. Maybe multiple stage, maybe only 2 stages, and so on. In this example, we have 12 flip-flops. Each one of them is replaced by this design. Actually, we didn't completely replace it. We just added a single 2-to-1 mux. Single 2-to-1 multiplexer. This multiplexer will have a selector, it's called a scan. If you are in the scan mode, so you have one here, the input that will go to the flip-flop is the serial input. If it is 0, then it will be D, and the flip-flop or the sequential circuit works its functionality normal. Now, if we want to zoom in inside this design and see how it is made, here are 2 ways that this could be done. One way is actually we have the design of the flip-flop, and we talked about it before. It's master-slave latches, as you can see here. The only difference here is that we added the mux, the multiplexer, and this multiplexer is actually, we design it using transmission gates, as we explained before. Another way to do it is by choosing the right clock. Again, we have the same master-slave latches. So from the X onward, they are the same. The difference here, you choose the D and the serial input by the clock itself. So if you feed the phi D, meaning the clock of the normal input, the D will go inside and the flip-flop will catch its value and watch it, store it, or transparent based on the value of the clock. If you are passing the clock of the scan, phi S, then the serial input is the one that is going to be transparent or stored within the flip. Now, to get the value of phi D and of phi S, it is actually by using this simple circuitry where you have a phi and the scan. If the scan is equal to 1, meaning this will be 1 and this will be 0. If this is 1, no matter what you give to it, here phi, that result will be 1. So you are not clocking, it's static 1. Here, since it is 0, the phi will go to the phi of S and the clocking will happen here, and the serial input will go inside the flip-flops, or you will be in the scan. If the scan is 0, now it's the other way around. You will have 0 here and 1 here, and you will actually select the clock to be 5D. 5D will work, and the D will go inside. Now, this is the implementation of this circuit. And by only adding this multiplexer, whatever way you want to choose, you can make testing the sequential circuits very easy. The combinational circuit, we give you an example, and we found out how to find the test vectors, and even there are tools that can help you with this. But for the sequential circuit, we have to do this, only adding this simple multiplexer. Now, the scan modes, you will first scan in, and this is the example, the 12 flip-flops, or the 12 flip-flop sequential circuit. You can see the multiplexer everywhere here. Again, the selector is actually the scan, same idea that we just explained. the input here for the first one is the serial input. And here you have the D for this flip-flop. Each flip-flop has its own D. And this D, it's based actually in the next state function of the sequential circuit. Here, 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 all the way in every one of them. You also can have the scan-in. To do the testing at the beginning, you choose to be in the scan-in mode, meaning the selector here will be one across all the multiplexers. If this happens, you are actually feeding the test vectors that you want to feed, and you will need 12 cycles to push them all the way to all the flip-flops. And you can see what you are doing here is a shift register. You are shifting the value in all of them. Once you're done with scanning in, you stop the scan in and you go to the normal mode. So you change the selector value and make it 0 for all of them. If it is 0, the D will go inside the logic cloud for each flip-flop, and the sequential circuit will work its functionality, and it gives you the result, and it's actually stored inside the flip-flop. So the flip-flops at the beginning of the normal mode will have the test vector that you chose. And once you give it more cycles and more cycles, you can give it as many cycles as you want based on the functionality of this circuit until you reach to, or you are satisfied with the number of cycles. You should be able at the end of these numbers of cycles to know what to expect in the output of the flip-flops. So it's changed each flip-flop, or these flip-flops will change their value as you are adding more clocks or more clock cycles. And at the end, you will reach to a certain state for these flip-flops. After that, you can scan out or push this result out by adding in the scan-in maybe 0 or 1, whatever you like in the scan-in, and you give it 12 cycles and you read 12 bits in the scan-out. This scan-out is the real output of the flip-flops after you do the test, and you can compare this signature with what you expect to do the testing. So we need a way to do the test vectors, to get the right test vectors. Either you do what we explained in the combinational logic, which will take a lot of time to get the right number of test vectors. And for a really big circuit, the number of test vectors will be huge to test the circuit. And there are other problems like maskings and so on. But one way to generate these test vectors is to do it automatically, or basically random. You choose random numbers and make it your test vectors. To do this, you use the automatic test pattern generation, where test pattern generation happens automatically. The reason is because it's tedious, as I explained. It could be a huge number of test vectors if you do the what we explained in the combinational circuit. Now, the ATPG tools produce a good set of vectors for each block of combinational logic, and the scan change are used to control and observe the block, as we just see. You complete or the complete coverage requires a large number of test vectors, and this will in turn raise the cost of the test. So you should use maybe the boundaries, some number of random tests, and that would be enough for testing. And basically, this is why most of the companies, if not all of them, they give you warranty, because they didn't do the complete test. They didn't do the complete test. Most products actually settle for covering 90%, and this is amazing, I see. If they cover 90% of the potential stuck at faults, that's amazing. with the possibility of 10% that might slip through the cracks. And a certain user have a faulty device, and maybe he can call the company and do the recall, and they work with it. Now, we will talk about the built-in self-test. The built-in self-test is actually a mechanism that permits combinational logic block to test themselves. The first step for it is generating a random input as the test vector. We generate a random input. We call them pseudo-random inputs because they have a certain seed, and from that seed you get the random inputs. This is why we didn't call it random, we call it pseudo-random inputs. And then you combine the outputs into syndrome, and we are actually taking the word and the method also from the medical field. You combine the output into syndrome, and with high probability, block is fault-free if it produces the expected syndrome. So you will have a real syndrome and an expected syndrome, and you compare them against each other. But the first step here is to generate the random inputs. One way to generate random numbers is by using the linear feedback shift register as one of the pseudo-random sequence generation examples. So here we have, this is just an example, we have 3D flip-flops. And in these 3D flip-flops, if we didn't have the XOR, it's simply a shift register with the property that the output of the last one is actually fed to the input of the first one, and you keep shifting. The value of the flip-flops will keep shifting and repeating and so on. If you add an XOR, an exclusive OR gate, you can have a pseudo-random sequence generation. Let's look at this table and see how do we do this. If we do the at the beginning, we made sure that the flip-flop have the values 1, 1, and 1. This is what will happen, and I indicated by the arrows. If you have these two or these blue arrows that goes this way, you are just basically shifting the value. If it is like this, it means that this is the XOR inputs, and they will generate a certain output for it. And this is what we have here. This is Q0, Q1, and Q2. I write it down like this. Q0 is the least significant, followed by Q1, followed by Q2. This is 1, 1, 1. So the value of Q1 and Q2 in the next cycle is always taking the value from the previous Q0 and Q1. And this is exactly what's happening here. The value here, or the value in this flip-flop will be taken from this flip-flop, and the value here will be taken from this flip-flop. The one that depends on the XOR is the new value here, the new value, which is the value of Q0. This is why in Q0, every time we are taking the XOR of Q0 and Q2, and this is what we have, Q2 and Q0. So Q0 and Q2 here is 1 XOR 1, which is 0. These will be just shifted because you will shift here and shift here. From 1 to 2, you will take those two XOR. 0 XOR 1 is 1, and you shift these two. Now 1 XOR 1 is 0, and you shift these two. 0 XOR 0 is 0, and you shift these two. 0 XOR 1 is 1, and you shift these two, and so on. 1 XOR with 0 is 1, and you shift these two, and you can continue forever. But if you start with 1, 1, 1, the next one, based on the calculation, is 0, 1, 1. We can write its decimal value to understand. This is the decimal value for the first 7. So the first random number is 7. And by the way, since you have only 3 bits, the numbers could be from 0 to 7 only. So the first random number that you chose is 7. The second is 6. The number after that is 5. And then you have 2. And then you have 4. and then you have 1. You can see that they are kind of random. And then after that, you have 3. And then you again reach 2 and the number 7. So you repeat the sequence now. So even if you continue, you keep continuing, you will get the same result. So this will be your random or the pseudo-random sequence that you will have if you use this hardware. Again, this is not a shift register, it's a linear feedback shift register because of the existence of this XOR. There is also, I want to give you another example. It's called the CRC checksum. It's actually for detecting errors more than having a random number, but it uses the similar ID. It uses the similar ID. You have here 5 inputs or 5 flip-flops. It's actually could be generated or it could be represented as a polynomial this way. So the hardware, it could be generated using a polynomial. So if the polynomial is 1 or x to the power of 2 or x to the power of 4 or x to the power of 5, the power of 2 or the power in the x's is actually giving you the or the information that it gives you is where is the location of the XORs. It gives you some information. The first information that can give you is the number of bits that you have, the number of flip-flops that you have. So here it's 5. Since the maximum power is 5, so they will be 1, 2, 3, 4, and 5. Now it's like the 1 here and the x to the power of 5 is giving you the edges of your design. That's the first one, and that's the fifth. These are the flip-flops. Now, where are the XORs in the design? If you see the power here, there are 2 and 4. So it will be the XOR before x to the power of 2 and before the x to the power of 4 if you start from x0. x0, x1, and x2, and x3, and x4. So the exclusive OR is before x2 and before x4. So from this polynomial, we can get the hardware. To do the CRC, we have another exclusive OR here, and you have the inputs and the outputs. The idea here is at the beginning, both switches, this switch and this switch, will be in the solid positions. The input will go to the output directly. So the input will go to the output directly. And at the same time, it will go through this linear feedback shift register to calculate the CRC. Now, this behavior here is the same as the pseudo-random sequence generation that we just explained. Now, after you're done with generating the CRC value, you will both change the switch 1 and switch 2 to the dotted position. If you change switch to the dotted position, you are no longer working with the linear feedback shift register, and you will just switch this line here to get the last values that you calculated, which is the CRC, and embed it right after the output. That's the idea here. You can calculate it if you have a polynomial, and let's say that you have this message that you want to check its CRC. The message originally was a bunch of zeros and ones. You shift them to the left by 5 to give a space for the result of the CRC, the value that will be stored in the flip-flop after you do the CRC calculation. And this division is actually not the one that you think that you studied maybe in the elementary school. It's using exclusive for. So for this one, you will choose here x to be 9. If you multiply x9 with x5, you will have x14, and you keep doing it for the others. So it will be x13, x11, and x9. And you do exclusive OR. The exclusive OR, if they are the same power exists, you cross it out. If not, you just drop it. You drop it and so on. And then you drop the next one and you do the same. Drop the next one and you do the same, and so on. You will have a quotient value, and you will have at the end, when you're done, the remainder value. The remainder here, R or Rx, is actually the CRC. Now, for us, this is only one of the pseudo-random number generation. And you can see that every time, every division, you have a sequence that is stored within the flip-flops. This sequence could be random. We could think of it as a random number, and we can use it as a test vector. So let's have an example to understand this better. If you have this message, which is the same as the one that we use in the division, x5, x7, x8, x12, and x4, represented by 101, 1000, 101. So at 5, you have a 1. This is bit 0, 1, 2, 3, 4, 5. 6 is supposed to be 0 because it's not shown. 7 is 1, 8 is 1. And the rest is 0 until you get the 12. 13 is 0 and 14 is 1. And at the beginning, this value will be 0, 0, 0, 0, 0. And after you finish finding the CRC value, you're supposed to have the remainder value right there. And the remainder value is actually x, x2, and x3. So it will be in position of 0, 0, position of 1, 0, position of, position of 1 is 1, since we have x. Position of 2 is 1, position of 3 is 1, position of 4 is 0. So this will be your remainder value once you're done with the finding the CRC. And this is exactly what we found at the end. You can see here, and from x0 to x4, at the end we got 0, 1, 1, 1, and 0. So how we do that? We basically do the same. Remember, I used the blue line to indicate the shift, and the red lines to indicate the exclusive OR. Exclusive OR. Now, to generate the table or generate this value, and to exactly know when to stop to get the remainder, you just plug in your message or your input right there. So you have 101, 101, and by the way, you need to start from the most significant bit. So it's 101, 001, or 0001, 101, 101, 0001, 101, and that's it. After that, you stop the calculation. The last step is just giving you the value of the random or the CRC value. Okay, so how we do this? I added a column here. What you need is x0, x1, x2, 3, and 4 indicated by the flip-flops and the inputs to tell you when to stop. I just added this column to make the calculation easier for you. And this is basically, this column is the input, which is this one, exclusive or with x4, which is this. So this column to give you the result of this value. The reason I'm doing this is because this input here is coming from the output of this exclusive core, and this one is also coming from the output of this exclusive core. So in the beginning, you would say I started with zeros. I calculated x4, which is 0, XOR with 1, the first input, and the result is 1. And then I shift this amount, I shift this amount, and I also shift this amount. Now to get the value here, you do the XOR of this value with this value. Remember that, or here, we get it 2 times, here and there. So we get it the first time here, and the second time right there. So you exclude, or you do the XOR of 0 and 1, which is going to be equal to 1, And for 0 and 1 also is equal to 1. And now you're done with the first, or with the clock number 1. You do the same for the next clock. I'll do it one more time. So first you get the value here, which will be the exclusive OR of 1 and, it's actually the exclusive one, the XOR of this one, which is X4, 1 with 0. So 1 with 0, the XOR of 1 and 0 is equal to 1. So you get this value. Okay. You get this value. And now you need to calculate what's in here. So what you do is you just shift the value of this one here. So this will be 1. This will be 1. Also, this one will be 1. So the one here will go right there. Now you just need to calculate this one and this one. And you do it by doing the XOR of 1 with 1 with the value here, 0. So 1 and 0 is equal to 1, and 1 and 0 here is equal to 1, and this way we got this number. As you can see, this from our perspective. Anyway, you continue doing this until you reach to the value here, and you can check it yourself. But for us to do the sequence number generation, that's our first random number, which is 0. The second random number is this one. And then after that, you have this number, and this number, and this number, and so on. And you keep repeating this until you have a repetition. Since you have 5 flip-flops, the numbers that you can generate, the maximum number that you can generate as random numbers is 32, maybe less. Now, after understanding the linear feedback shift register and how to generate a random or a pseudo-random number as a test vector, we can discuss the PELB, which is the built-in logic block observer. It's actually combined the scanning with the pseudo-random sequence generation and also the signature analysis. This is the design. You have a flip-flop, 3 flip-flops in this case, and either you get the normal mode where the D go in the flip-flops, or you have other modes. The modes that we have is the scan, the test, the reset, and the norm. And you have C0 and C1 to indicate which mode you are in right now. To understand this better and why we have these gates here, we will check it one by one, starting with the first step, which is the reset. When you have 0 and 1 in the horizontal lines here. So if you have 0 and 1, this 0 will be entered in this and this and this and the result will be 0 for each one of these ands. Remember, this is called the reset mode, meaning that we want to put zeros in the flip-flops. So this is 0, 0, and also 0. Now, this one, after the bubble here will be 0, and if it is in the AND circuit, and it's a 0, also the output here would be 0, and 0, and also 0. The XOR, if you have 0 and 0, the result of it is 0, which means that all the flip-flop, the D value of the flip-flop will be equal to 0. Also, this one is going to the this multiplexer, and it will choose 0, or sorry, it will choose the serial input. It will choose the serial input. But no matter what serial input actually you are given, this result will always be 0 because you have 1 here, and the one after the inverter will be 0, so that the result would be 0 irrespective of this value. In this way, you reset the flip-flops. That's the first step. The second step, where you, after the reset, you should generate the pseudo-random sequence by using the pseudo-random sequence generator. And we built it within the circuit itself. So in the bell, what actually we did, we have the sequential circuit, we have the combinational logic right over there, and it gives us D0, D1, and D2, and we also have the flip-flops as well. Instead of having a simple multiplexer, we are adding these gates. Or you could think about it this way, just from the sequential circuit, take out all the flip-flops and plug in this hardware right in the in replacement of the flip-flops. If you do that, then you will have the bell scan. We did the reset, and now we will do the scan. The scan, notice that you have a 0 here and a 0 here. The only change is this 0 here. And because the value here is 0, after the bubble, it will be 1. Similarly here and here. And the value will be whatever value you have. Also, you have here is 0, and the 0 will choose the feedback. So it will be whatever value you are generating from this feedback using the linear feedback shift resistor. And it will go this way. Also, the XOR, since you have a 0 here and F0, the result of it is F0. So it's like it's just a buffer here and here and here. So what exactly you're doing, you have the 3 flip-flops with 1 exclusive OR, and you can generate a random number based on how many clocks you have. So the next step would be the scan. So you scan in the first, after having the reset, the value is 0, 0, 0. You do it, the pseudo-random normal generating using the linear feedback shift register, and you have a certain random sequence in the flip-flop as a test vector. The next step is to use the normal mode. And in the normal mode, it will be 1 here and 1 here. If you have a 1 here, what you are actually having, you have after the flip-flops a 0. You have here also a 0, and here a 0, meaning that the value of this AND is 0, and it's like not there. It's always 0 in this input. And because this is 1, what you are inputting here is the value of D0 and D1 and D2. After that, you will have the also, because you have a 1 here, you are not having the feedback, so there is no feedback coming here. You just plug in the normal mode, you plug in the D's into the flip-flops, and it should work, or the sequential circuit work normally within the logic cloud. Now, after this, the next step is the test mode. The test mode, what you are doing is the signature analysis, meaning that you are testing the D's with the F's. So what you do, you have 1 and 0 here. We know that the 1 will generate the D's for us, and the 0 will generate the F's right there. And now you can use the XOR as a equality comparator. Is the D0 equal to F0 that I expected? The D0 will be the actual value, and the F0 will be the expected value. And then you can have the comparison here, and you get the result. And so this is the idea of the bell design for testability. Now we will talk about the last point, which is the boundary scan. In the boundary scan, testing board is also, as we said, difficult, even with boards. So you need to verify the solder joints are good, the driving a pin to 0, then to 1 to make sure that they are correct at the solder points or the external pins. You check that all connected pins gets the value. The through-hole boards used bed of nails. You can see that here we have different packaging styles. This is the surface mount where you service it against the board itself. And you have the through hole where it goes or penetrate the board through certain holes within the green boards or within the PCB, the printed circuit boards. So if you use the surface mount technology, this one, and the BGA, which is the ball grids, these are balls that go again against the board itself. You cannot easily contact the pins on the PC. But you need to do it for testing. And there is a way, which is the boundary scan that we will explain in the next slide. You build capability of observing and control pins into each chips to make the board test easy. So if it is through hole, even the service mount, since you can access these pins, you can actually test it. But if it's right there, like this one, and you are actually putting it in the board, you cannot access these pins. It's very difficult. Or even the BGAs, it's very difficult. So if that's the case, one way to do it is by using the boundary scan, where you actually have one input, choose whatever input. It's actually done by the architecture designers. They choose one input and they make it the serial data in, and you have to go across all the pins. And you get out, now you have covered all the pins. Again, get in from a certain place, go across all the pins, and so on, crossing all the pins, enter from a certain bin, and get out from the bin just next to it, cover all the pins. Now, if you have, in this example, ship A, B, C, and D with certain connectivity to do the functionality of the ship, what you do is you can use the serial data in and you plug it in within all the pins by certain number of clock cycles that is equal to the number of pins in all the chips. So you clock in all the serial data in, and then you do the normal testing, and after that you get the serial data out to get the signature of the that test, and you can compare it against what you expect and check if the testing is correct or having a problem. So basically, the boundary scan, you try to shift through all the pins. To do the boundary scan correctly, here are some of the things that you need to make sure that they exist. You need a test clock. So one of the pins, you should make it for the test clock. Sometimes in some circuits, they use the system clock as well. But if you want to have a slower test clock to make sure things are properly tested, you can. You have also the TMS, which is the test mode select. So either test mode or normal mode. You have the TDI and TDO for the serial in and the serial out. And you could have a test reset, which is optional here. You can see here that we make sure that we have these four in this design. You have the TDI going in, shifting all the pins, and then you have the TDO or the test data out. And you have the test clock also and the test mode select as well. So what happens again, the same idea for this chip. You serially input the test vector, and you need 10 clock cycles, since the number of pins here is 10, to plug in all the test vector bits. And then you work on the test. You have to switch to the normal mode. And after that, you get the values that within the pins after you finish the test and shift them out by going again to test mode and entering a value of 0 just to push the values outside and check if you are having what you expect or not. There are ICs that can help you do all of this. It's called testers ICs, and these are some examples for them. This is can test 4 chips together at once, and here you can test only one. And there are many examples. This is for just one tool that could help you, a hardware tool that can do the test for you. It's from Testostar IC. The Testostar IC, it has a brain box where you can have 4 at the same time, or you have this one. And there are many other examples. In summary, think about testing from the beginning. Simulate as you go and plan for tests after the fabrication. Remember this, if you don't test it, it won't work, guaranteed. This is not only for the electronic circuits, even in real life. And with that note, I'll stop here. And this will be the end of the design of testability. Next time, we will talk about some aspects or some circuit pitfalls where we will treat them as a patient, and we will try to remedy the situation and rectify the problem that they have.